Welcome to Data Management for Graduate Students. This is part of a series of workshops we're having for graduate students. We had a data literacy session last Tuesday. Today's data management. Next week will be data wrangling, data cleaning, data visualization, and following up with data sharing. All our material will be shared on our YouTube channel. So if you missed something or want to review, you can always check there. And registration is required so that you can get the Zoom link. Anything on these slides, I will share the slides with you after, so don't worry about tracking down all the links I'm sharing. You'll get them when you get the slides after our session is over. For those of you who are new to campus, hello? For those new to campus, I wanted to introduce our data services team. Again, we're in Olin Library. There's 4 of us with another 2 on the way. And some of the services that we support are data exploration and visualization, data management and sharing, which is really what we're talking about today, data sourcing, digital humanities, GIS, and 3D and extended reality. We're located on the A level of Olin Library, right below Whispers. And next door to us is the research studio that has specialized software for working with data, like ArcPro for GIS data that only works on PCs, plus Atlas TI and NVivo for quantitative data, and a bunch of other software as well. You can access the machines in person, or you can remote in at any time. For hours and reservations, please visit our website. We also run a help desk. You can drop in hours in person or come on Zoom, or you can book an appointment with one of us and we'll get back to you with a suitable time to meet in person or on Zoom and go over your issue. Again, you can look at our website for details on how to get the Zoom or book an appointment. So what are we going to cover today? Well, first we're going to talk about why we care about data management, what to include in a data management plan, good practice for organizing and naming your files, and what makes good data documentation. So when we talk about data management, we're often really talking about project and data management. And a little time now, planning things out is going to save you a ton of time later. The current you and the future you, if the current you does your job, the future you will be very happy. A little bit of time you save now is going to be huge. And it's not just for you, but it's also for your lab mates and other researchers. So why might you develop a plan? Well, I keep emphasizing the saves time in the long run, but really what it is gives you access and understanding your data more easily, both now and in the future when you haven't worked with it in a while. So think about a document you put down for 6 months, you come back to it, and you don't even remember what you did 6 months ago. Now imagine that the new postdoc comes in 2 years later, and you have to explain to them this document. Well, it's even harder for the postdoc who wasn't part of it in the first place. So it's the kind of thing that just helps the team move more smoothly, maintain continuity through staff changes. You're going to maintain data integrity, reduce the risk of lost, stolen, or misused data. It helps you validate your results and reproduce them, facilitates the sharing of your data, which can lead to greater collaboration and impact, and it reduces the time to write up your research results for publication. As your project progresses, you may find it necessary to revisit your data management plan and make changes. That's okay. It's not something to be fixed. And if you haven't made one yet, it's never too late to make one. So why does good data management matter? Again, you can start building on existing research at reduced costs rather than redoing work unnecessarily. You can understand the meaning of the numbers represented and have an insight into when the numbers and the arguments don't match. Otherwise, when you take data arguments at face value, you may come to faulty conclusions. You want to be able to show your methods and stand behind your data and design a reproducible research project, because the last thing you want is to have to retract something. You want to be able to argue your point with solid data, rather than not have grounds to defend your hypothesis. And sharing data improves your data citation and encourages confidence in your work. When we hide our data, it's useless to others and can't be cited, and not sharing can weaken your findings. Now, I'd like to share with you this 5-minute video. I'm going to turn on the captions for you, which should help. It's got a computer-generated voice, so it might be a little hard to understand.
Hello. My name is Dr. Judy Benign. I'm an oncologist at NYU School of Medicine.
Hello, Dr. Judy Benign.
I read your article on B-cell function. I think that I could use the data for my work on pancreatic cancer.
I am not an oncologist.
I know, but I think I could use the data for my work on pancreatic cancer. Do you have the data?
Everything you need to know is in the article.
No. What I need is the data. Will you share your data?
I am not sure that will be possible.
But your work is in PubMed Central and was funded by NIH.
That is true.
And it was published in Science, which requires that you share your data.
I did publish in Science.
Then I am requesting your data. Can I have a copy of your data?
I am not sure where my data is.
But surely you saved your data.
I did. I saved it on a USB drive.
Where is the USB drive?
It is in a box. It is in a box at home. I just moved.
But can I use your data?
There are many boxes. So many boxes. I forgot to label the boxes.
Hello again. Thank you for sending me a copy of your data on a USB drive. I received the envelope yesterday.
You are welcome, but I will need that back when you are finished. That is my only copy.
I did have a question.
What is your question? You might find the answer in my article.
No. I received the data, but when I opened it up, it was in hexadecimal.
Yes, that is right.
I cannot read hexadecimal.
You asked for my data and I gave it to you. I have done what you asked.
But is there a way to read the hexadecimal?
You will need the program that created the hexadecimal file.
Yes, I will. What is the name of the program?
Cytosynth.
I do not know this program.
It was a very good program. The company that made the program went bankrupt in 2007.
Do you have a copy of the program?
I do not use this program anymore because the company that made it went bankrupt. Maybe you can buy a copy on eBay.
I have good news.
You again.
I talked to my colleague. She knew a person with a copy of the software.
Then why do you need me? Everything you need to know about the data is in the article.
I opened the data and I could not understand it.
If you have the program, you will find it is clear.
Well, I noticed that you called your data fields SAM. Is that an abbreviation?
Yes, it is an abbreviation of my co-author's name. His name is Samuel Lee. We call him Sam.
I see. And what is the content of the field called SAM1?
Ah yes, SAM1 is the level of CXCR4 expression.
And what is the content of the field called SAM2?
That is logical if you think about it.
What is the content of the field called SAM2?
I don't remember.
What about SAM3? Is there a guide to the data anywhere?
Yes, of course. It is the article that is published in Science.
The article does not tell me what the field names mean. Is there any record of what these field names mean?
Yes. My co-author knows what the content of SAM2 is, and SAM3. And SAM4.
Can I talk to your co-author?
I'm not sure.
I would very much like to talk to your co-author.
Well, he was a graduate student. He went back to China 2 years ago.
Can I have his contact information?
He is in China. His name is Sam Lee.
I think I cannot use your data.
You could check the article to see if what you need is there.
Please stop talking now.
So I absolutely love that video. It's an all too common problem that we have in academic research. And so that's why it's so important to come up with a data management plan so that these things don't happen. So in general, what's in a data management plan? You're going to look at for what do you collect? How are you going to collaborate? How are you going to document everything? How are you going to organize, store, and protect your files? And how will you share it? The more you do in the planning stages, the easier it will be to deal with later. A data management plan is a living document, so it should change as needed throughout the life of the project. You shouldn't think that it's something you just do at the beginning when applying for funding. It's really something that should be in active use throughout the course of the project. Have it written down and be intentional about how the data will be collected, organized, and stored. Don't necessarily just do the thing you did last time. Think about it as for each project. So you want to set rules, guidelines, boundaries. It's important to have these conversations at the beginning of your project rather than later because things can change. Change either in the personnel or the team dynamic. Who's going to take primary ownership of the data? Do we still retain ownership of the data once we leave the organization? Should we notify each other when we intend to share our data, or can we share it as we please without consent? For those that, since you're in graduate school, is really important for you in particular to check with your PI if you want to use lab data in your dissertation. You need to make sure that the PI is okay with that. And you don't, if you don't know now, you better ask, because the last thing you want to do is be in the last year of your PhD program and have to lose a whole chapter because you're not allowed to share that data. You want to agree on platforms and applications that you're going to use. Again, there's no sort of one size fits all. The important thing is to agree upon it. So if you want to use Microsoft OneDrive, that's fine. Don't also save files on Google Drive and mix and match. It's important to sort of keep things in one place. Have storage and backups, multiple copies, geographically varied, different media. In library land, we talk about locks. Lots of copies keeps stuff safe. The last thing you want is to have everything saved on a single hard drive or a thumb drive and not be able to be found. Like in our little video, he only had things on a thumb drive. So what to look for when you're evaluating storage locations? You want to look for routine and automatic backups with some built-in security profiles, passwords and such, accessible by the team. So that means don't just save things on a local computer, external hard drive, or thumb drive. Instead, use the options available to you. There's our RIS network server, there's Box, and RIS also offers HIPAA compliant storage. Practice good security hygiene. Agree on who has access, create strong passwords, share passwords on a need-to-know basis, and disable them when that need ends. So it's not just a matter of badging in and out to get to the lab, but also think of the equivalent for accessing online materials, your digital materials. The last thing you want is someone on the team to disappear or lose their passwords or still have access to something that they shouldn't have access to. Bad things can happen. So this is a way to keep your data secure. And it doesn't mean anyone is acting maliciously. Sometimes it can just be forgetfulness. But if you practice good security hygiene, things should go better for you. Think about what type and format of the data do you have, not just to answer the research questions before you, but how to manage a project. So your data types Might be things like medical history, case reports, images, raw data, process data, but also project management, meeting minutes, email, Slack threads, your correspondence with the institutional review board. Maybe you have a folder of literature review. All those are different types of data, either for yourself or your team, that you want to be able to keep track of. And they can come in any number of formats. So you should be sort of alert to both kinds of things out there. We typically recommend that you store things in open source formats because they are the most sustainable and can be read by many different systems, so that you don't run into the problem that we had with the video where you're using proprietary software that's not available anymore. Learn to recognize sensitive data. This is data that's restricted by law, university policy, or ethical considerations. Could be confidential business data, could be personally identifiable information like social security numbers, credit card numbers. It could be protected health information like the 18 HIPAA identifiers or FERPA data. And really just any information that puts research participants or locations at risk. It's important that you think through those use cases in advance before you get yourself in trouble. So what is your plan for handling sensitive data? Where are you going to store it? Who can you share it with? Is there a data use agreement? Is there restricted access? What have you promised the institutional review board that you're going to do? And are you doing it? Does your informed consent cover all the bases? Do you plan to de-identify your data, and how? These are all the types of things you should be thinking of and planning for. On this slide are some more resources for dealing with sensitive data. I'm not going to go through them right now, but I will be sharing all the slides with you and you can follow up later. It's important to organize your files well, come up with a directory structure. And what's also useful is keep a blank copy of the structure that can easily be copied into another project. There's different ways you can organize it. I don't want to pretend that there's only one way. What's important, though, is that you be consistent with it. It's also important not to go through too deep. About 3 or 4 levels is good. You don't want to have to click through 10 folders to find your data. That's not helpful to anyone. And you also don't want to rely on nested folders when naming your folders and files. So here's some naming convention best practices, both for folder names and for files. You want to keep it brief, around 32 characters max, but also meaningful. Don't rely on nested folders. I'll explain what I mean by that in a bit. Use a consistent structure. Use dates in the international accepted format of year, month, day. List your versions alphanumerically, like V1, not just 1, so people understand what that number means. Do not use spaces in your file or folder names, and no special characters. It's really important, the spaces and special characters. Some systems don't work well with spaces in the file names or directory names. It can cause a lot of confusion. So the best thing to do is just avoid it altogether and use underscore instead. When you create meaningful file names, it's much more easily to locate them. Obscure file names can be difficult to locate in the future. So let's go through some examples. In the bad example on the left, what's going on here is really addressing this nested file issue. If the January CSV from 2021 and the January CSV from the 2020 folders get mixed up somehow, you don't have a way to tell from the file name alone what folder they belong to. So that can happen over and over and over again, especially as your data set grows. So much better practice would be to sort of prefix everything. So here we have project name, and I just abbreviated that to PN, and this is my raw data file. And then I have a raw data 2020 folder, and then I add PN raw 2020 February to the file name. Now, if I get these files mixed up and the directory structure somehow moves around, I know exactly which files are which. The important thing is really just to be consistent with your file names so that things can be found in the future. So for example, the US Census Bureau convention uses a starts with the type of survey, underscore, the date, underscore, the range, underscore, and a table ID. Or in another example, if you're creating your own, this one has 5 components. The first one is a project abbreviation. The second component is the type of resource. The third component is the coverage. The fourth one is who made the file or modified it. And the last one is the modified date. So think through, as you're developing your convention for your team, think about what data you have, what threads through every data type in a folder, and how you want to handle versions. So with versions, we're all guilty of this, where we do things like draft, final, no, this is the final, and add those 2 things. That's not helping anyone. In the examples on the bottom, we're using the version numbering, alphanumeric version numbering, or adding a date field in there. All of those will work for you much better than final type things that we're all prone to doing. There are version control systems out there, GitHub, which is for code, but doesn't just have to be for code. It also works well as a project management system itself. You can keep track of versioning in Box, and you can keep track in the Google system as well. And not everyone knows that in the Google Suite, you can actually go back and name your versions as well. So you don't have to just look at the timestamp. So what is good documentation? Good documentation describes 4 things: the source, purpose, and method of collection, the variables and units of measure you're using. It has a file inventory, and it describes any processes involved in data cleanup and analysis. Good documentation typically comes in one of these 3 types. It could be a README file, it could be a data dictionary, or a code book. README files are especially common in coding systems, but they're not the only people who use README files. Data dictionaries and code books you often see in qualitative research, but again, they're not the only people who use those. So a README file typically is just a plain text document with title, author, name, contact information, description, rights of reuse, an inventory of the files, and a brief description of what they might do, the dates of data collection methods, any related information, related journal article, related code, previous data set, and any software, hardware dependencies. We have a README template available in our library guide to the WashU Research Data Repository. And you should always be saving these as a plain text file at the top level of your folder, so it's the first thing that someone sees. A data dictionary is a bit similar. Here's an example of one, and there are many tools that help you make these. What's useful about these is it's very explicit in the variable name, sort of the short name that might be included in a column name, and its full name and description. It's got a measurement unit, so you can distinguish between numeric values and date values and text values. And then it also has an allowed values column. So this is important when you want to understand the possible ranges, say. So you're dealing with adults, ages should be 18 and up. And it helps you to easily spot flawed data. So if you see an age that's 16, well, there's something wrong with that. That's not one of the allowed values for this field. So if you work in REDCap, for example, it can help you make data dictionaries. Oops. And then there's a code book. This is an excerpt from the ICPSR Guide to Social Science Data. And this presents an example of the kind of scheme from the Census Bureau again. The first digit of the scheme describes the number of parents present in the household. The second indicates the employment status of parents, and the third tells whether employed parents work full or part-time. So this is literally why it's called a code book, because the code 111 means both parents at work 35 or more hours. The code 112 means father only at work 35 or more hours, and so on. There are resources out there for preparing any of one of these data documentation types. The Cornell site has a really good README template. The data dictionary lesson from Open Science Foundation is very good. And the ICPSR Guide to Code Books is quite excellent. If you need help putting any of these together, you're welcome to contact Data Services. So now I'm going to dive a little deeper into the files and maybe what your data looks like. You want to have a data strategy and a structure. So for example, you're taking readings at a particular site. And here, column 1 is a site ID. So do you want the record to be each site? Or do you want the record to be the sample taken at the site? So in this example, it's similar data, but instead we're organizing it by the sample that was taken rather than the site ID. So again, you have to really think through what makes sense for your project. Do you want your record to be, for example, the patient or each clinical visit? Do you want it to be a case number or service received? Is it the author or is it the publication? So when in doubt, usually helps to go more granular, and then you can always aggregate or summarize later. These kinds of things help you keep track of your data and just not having to sort of reorganize things as you go forward. But to be fair, sometimes you don't realize your data strategy until you get going on your project. So again, go back and revisit things and be like, oh, my original structure doesn't quite work for what I actually want to accomplish. I'm going to have to rearrange things a bit, and that's fine. Just be intentional about it. So technically correct data, we refer to as data that can be read or analyzed by a computer. You might have heard this referred to sometimes as tidy data. So we want each observation in its own row, each variable in its own column. Are the data types correct? So are numbers treated as numbers? Are dates treated as dates? Text as text? This is tricky with things like zip codes. Zip codes might look like numbers, but since they're not meant to be added or subtracted or perform mathematical functions on, maybe they're better off being represented as text. Are there any extra characters or spaces that might interfere with analysis? So this goes back to our file naming convention. The data cleaning workshop next week will talk more about getting your data in shape to be technically correct data. And then you also want to look for consistent data. So this is data that's ready for analysis or statistical inference. So are the values free, error-free, and complete as possible? Should missing values be imputed, deleted, or ignored? Do the values make sense in your data context? Check that the values live in the expected universe. Again, if you're analyzing adult patients and you have a 16-year-old, something's wrong. Or if you have a 150-year-old, something's wrong. And check the relationship to be between values and see that they make sense. You're also going to have to deal with missing data. It does happen. So in a spreadsheet, how many times have you opened up a spreadsheet and seen an empty cell? Well, does that empty cell mean 0? Does it mean null? Or does it mean not available? It's really important to understand that, because you don't know how to rely on the data in there or how to deal with those blank cells without more instruction from the data producer. So we don't want that to happen. So missing data can happen, it can be a processing error, like a data entry problem, not applicable, and refuse to answer, you might typically find in social science survey type research where the respondent didn't give an answer or the question wasn't applicable to them. And sometimes there's just no data available. The sensor was broken that day. And so you didn't get the measurement that you needed for that day. It happens. So the question is, what are you going to do about it? So it's important to record in your data management plan how you're treating these missing data values. There are different statistical methods you could take to impute missing data, assigning the average or most common value. Different disciplines have different approaches, so I can't tell you now which one you should use. The important thing is to document what you've done and to indicate when the data is being imputed and not directly measured. Other disciplines might ignore missing data or delete the applicable row altogether. At the end of the project, we want to share our data and we want to ensure that the data is fair, F-A-R. It's findable, so in an indexed repository, like the WashU Research Data Depository, given a unique persistent identifier, like a DOI, and has rich metadata. That it's accessible in a repo that uses open standard protocols. Again, the WashU Data Repository is one of those that meets federal standards for repositories. Interoperable, so we want to use as much as we can standard open formats, non-proprietary. That way, that ensures that any person or tool can open that type of file. And we want it reusable. So when it's well documented, has good provenance, open licenses, that makes it much more likely that other researchers can use it. So if you stuck with your data management plan, achieving this goal and readying your data for deposit in a repository will go much more smoothly. If you haven't been following your plan all along and scrambling to make your data fair and deposit in a repository to meet your funder requirements, that's just a lot of more pain at the end of the day that you don't want. So really, there's just 4 things you have to remember. Have a plan. Be consistent with it. Create documentation and back everything up. If you can do all those things, you're in great shape. Now, I've talked a bit generically about data management planning. Now I want to turn specifically to data management plan, which is something we talk about when dealing with funding agencies. They're typically looking for a specific data management plan that might meet their unique criteria when evaluating your submission. And because each of the funders have peculiarities, the DMP tool was created. It allows you to select the relevant funder and division and provides a template that helps you write your plan. So I'll go over that just a little bit. Our last session on data sharing, we'll go over this more. It's available to WSTL key holders. Log in with your WSTL email to get access. And when you do, you'll see up front different guides between the Becker campus and the Olin campus for dealing with research data sharing. When you start a new plan, you can select the primary funding organization in the drop-down list, and then it auto-populates. And then you can also find then the subsidiary organization, helps you populate it. Then gives you the prompt for that specific organization and the template that that specific organization has provided. And then on the right side, you can see tools, again, for that specific funder, the guidelines for around award policies and procedures. This talks about the period of data retention. And you'll see here, we have created some boilerplate language on the right that you can cut and paste into, oops, I fast forwarded, into your data management plan about archiving material with the WashU data repository. So we made it easy for you to cut and paste which language applies to your project. We use the DataCite metadata schema to mint our DOIs. That's standard. And then this is an important feature and why it's important to log in with your WSDL key. You can request expert feedback. So we in Data Services or the Becker Medical Library are happy to review your data management plan and give you feedback on it before you send off your application. And finally, it makes it easier to download and incorporate into the rest of your grant application. So generally speaking, Library Data Services can help you by reviewing your data management plan. And I mean both the official one you might be submitting to a funder, as well as your project plan among your teammates. We can help you prepare README file or whatever data documentation you have to accompany your data. We're happy to consult on data cleaning and preparation. And we also offer access to licensed software for data management in our research studio. That includes things like Atlas TI, MATLAB, Oxygen MLL, and Vivo, an ArcGIS platform. So before we go, I have one request for you all to go get your ORCID ID if you have not already. It links your publications and other research activity to you. You can get a free ORCID identifier at that link, and it takes about a minute to set up. More and more publishers and funders are requiring it anyway, so get it out of the way now. But it does help you maintain control over sort of your ORCID record, your publication record, if you have a common name or you got married and you changed your name. It helps you distinguish yourself from the other people with a similar sounding name. Maybe you changed organizations and someone wants to know if it's the same person that was at WashU as at Stanford. Yes, that's the same person. So it also can save you time with repetitive data entry. So run out there and get that right away if you don't already have one. So that's the end of the presentation today. I am going to turn off the